Alright, so now let's move to a 3D example. Okay. Now the 3D example, as it turns out, will actually be easier to, the math will be easier. So let's see what it is like. Okay, so the wave equation remains exactly the same. The only thing to note now is that it's 3D. So of these 1, 2 and 3 terms, which terms will be different from before? Let's go first term. Will the first term be different? Well, it will be different because if I choose a coordinate system now, what coordinate system should I choose for a 3D problem? 3D spherical coordinates. That's the most natural, because if I put my like if I do the same choice that I did before, put the point source, the impulse at the origin, then there is perfect spherical symmetry for the problem, right? So then the rather than cylindrical coordinates, spherical coordinates is going to be the most intuitive coordinate system. So del squared will change, right? Earlier it was for polar 2D, now for 3D spherical, right? So yeah, I don't expect you to remember the form of del squared. So del squared has a lot of terms for theta dependence and phi dependence. We'll just keep the r dependent terms, and that's 1 by r square and dou by dou r squared dou by dou r. So this we just look up and use it. Okay, that's the operator. The second term remains as is. What about the third term? Third term, we just have to take care to know, to keep in mind that it's a 3D delta function. Okay. Earlier it was a 2D delta function, and even before that it was a 1D delta function. Okay. So that's just one thing that we have to keep in mind. And we'll just sort of repeat the recipe that we had previously. We will choose r greater than r naught, such that what happens is that I get a del squared g plus k squared g is equal to 0. Okay. So first I will solve this and then look at boundary conditions. Okay. So when I go to sort of solve this, let's put this in over here, right. So these partial derivatives go away, they become total derivatives, because there is no theta phi dependence. I have put my impulse at the origin, right. So let's see. So what I can do is, so this is 1 by r squared, okay, d by dr, r squared dg by dr plus k squared g is equal to 0. Okay. One small trick I will do is I will just multiply r everywhere. Okay. Now I can the only thing that I can sort of simplify in this is the first term, right. There is a derivative of something, so I can open up this. So two functions, product of two functions and derivative, right. So the first term will be, so I can take the derivative of r square, right. So I will get 2r dg by dr, and that r will get cancelled off. So I will get a 2 dg by dr, that is the first term. Then r yes, r into d2g by dr2, and the second term remains as is, k squared r g is equal to 0. All right. Now any ideas on how to further simplify this? So the hint is this, that we are looking at there are second order derivatives, that is the maximum order of derivative. You see a 2 term over here. So when you see a 2 term and a second derivative, what kind of a trick could you play? Could you write this whole expression as the second order derivative of something, of some function? I want to try to write it like this, d2 by dr2 something plus k squared rg is equal to 0. What might that something be? Actually, I made one mistake here. This should be r. Yeah, that one r got cancelled off. Yeah, definitely a g has to be there.
2r square g.
2r square g. No,
R
some.
square g.
What about simply rg? So this will have g, second derivative of g multiplied by r plus 2 times first derivative of each term plus g times second derivative of r, which is 0. Second derivative of r is 0, right. So you can just expand this over here. Do you want me to do it? Okay, fine. Yeah. So this manipulation has given me a equation that looks actually very familiar. What does this look like? Yeah, even simpler than Helmholtz equation. It's a simple harmonic oscillator model, right? I have second derivative of some function plus k squared this thing. So Rg is equal to sine k kind of a, or cos k, that kind of a thing works. The most general way of writing an oscillatory function is, instead of sine cos, what can I generalize that to? E to the j, right? So I can write down in the final form over here, this r, g of r, therefore should be equal to, it's a second order differential equation. So how many solutions are possible, independent solutions? 2. What are those 2? So I want to write down now this, right? So the first function will be, so e to the j is what we agreed. Okay, so let's make it more precise. E to the, what should I write? J kr. If I take second derivative of this function, what will I get? I will get a minus jk and then I will get a minus k squared, right? And a constant that is unknown. Is that all? Is that the only possible solution? Minus, right? That is the second independent solution. That will be a minus jkr, right? So I can just write this, take the r over here, and I have a right. So these kinds of functions are, what are they called? They are spherical plane waves. Unlike 1D plane waves, the amplitude of these functions, it decays as you go away from at larger and larger r, which is physically what you expect. If I place a impulse at the origin, if I go away, amplitude should decay, right. So again, now we know what tricks to play now, right. We can ask, of these 2 terms, can I eliminate at least one term by boundary conditions, right. So the trick is the time convention. So our time convention as before is e to the plus j omega t. So which term can I get rid of? A term, right, because a term will correspond to a incoming wave, right? So a is equal to 0, and so the final form that I have is g of r is equal to b e to the minus j k r by r. Okay. Okay. Now what remains is the constant b. Okay. By now you know the game. So we take this differential equation and do a volume integral on both sides. Okay. Even though I am putting one integral sign, I do mean a 3-dimensional integration. So what happens? Let's look at the first term. Okay, this is the first term. I can play the same trick that I had played previously, right. So I should try to write this as the divergence of something, right. So I can write del squared g as divergence of grad g, right, and then I have a over volume dv, right. So this will become what? Outward flux of grad g, right. So this will become grad g dot n hat ds. And what is my sort of problem setup? This is my xyz, and I have a sphere, right, v epsilon, right. It's a sphere, radius epsilon. Okay. What is the outward normal?
R.
Which is equal to r hat, because it's centered at the origin, right. So n hat is equal to r hat. Okay. Grad g, again this is only a r dependent problem. So this is only going to give me del g by del r hat. Okay. So what do I get from the first term over here? I get, so my constant b will be there over the surface, grad g, right. So what was my g? I will just write it over here, b e to the minus j k r by r. Okay. So I have to take the derivative of this guy with respect to r. So first term will be, let us say, minus j k e to the minus j k r by r. Okay. Second term will be derivative of 1 by r, which is minus 1 by r squared. Okay. What will ds be? What is ds? Surface r? No, you're not r dr d theta, that's 2d. In 3d, r squared sine theta d theta d phi. That's the surface differential element. I mean, on the surface of the sphere, that's the differential surface element. It's easy here because there is no theta phi dependence. So this integral over here is going to give me 4 pi. 4 pi is what I'm going to get out of it, right? Everything else inside the integrand is constant as a function of d theta d phi, right? So it's all going to just pop out over here. So what will it pop out to? So there's a minus sign on both these terms have a minus sign. So I can take that out. So I'll put a minus. I'll get a 4 pi from the integral. So I'll get a minus 4 pi b, right? And these two terms over here. So I'm going to get a j k e to the minus j k r by r plus e to the j k r by r squared, 0, sorry, not 0, evaluated at r is equal to epsilon, right. There was a r square also, right? Yeah, there's an r square also. Which of these terms will survive as I put, if I take epsilon tending to 0, which of these terms will survive? Only the second term, because r square cancels off. As r equals to epsilon and epsilon tends to 0, what happens? The first term goes to 0, second term survives, and what do I get? Minus 4 pi b. Okay, very good. So that was the first term. What about the second term? Second term, we will have to do this integral, right? So it's going to be k squared, and this is a volume integral, b e to the minus j k r by r, sorry, just by r, and r squared four pi dr, right? I have eliminated the theta and phi integral because there is no theta phi dependence. That will give me the 4 pi. So I'm left with this, and integration is from 0 to epsilon. Okay, is that clear? So I can take out all of these constants, 4 pi k squared b 0 to epsilon r e to the minus j k r dr. That's all that survives. Okay. So you can work this out. Okay, this is a very simple integration to do. Like before, I'm not going to actually do it. It's a very simple integral for you to do. What do you intuitively expect this answer to be? 0, right? How can you see this intuitively without actually doing the integration? Symmetry is not going to help you here. Any other argument? Yeah, the mod of the integrand is?
This is going to be r, and then going to integrate from 0 to epsilon, but epsilon will be 0 again. So
Yeah, okay. Another way of seeing it is that the integrand is something which is it always finite? It's always finite. and I'm integrating over a volume, so I'm going to get some finite quantity multiplied by the volume at best, right, and that volume is shrinking to 0. Now, if there was a delta function in here, then I have to pay a little bit more attention, like if it were a log or something, then I have to pay a little bit more attention. But here the integrand is finite, integrating over a finite volume which I will set to 0. So, these kinds of tricks you should use and just say that as epsilon tends to 0, this is equal to 0, okay, and you can manually verify by doing this integration. Right, and the third term is going to give us, so 3D delta function integrated over that volume, I should get -1, okay. So, the final expression that I will get is minus 4 pi b is equal to -1 and b is equal to 1 by 4 pi. So, g of r is equal to 1 by 4 pi r e to the minus j k r, that is it. So, once again we will, this was when I placed the impulse at the origin, but if I want to write it in general, what do? I will ask what is g of r prime. So, now I should write it in a little bit more careful way. So, I will have a 1 by 4 pi e to the minus j k r minus r prime divided by mod of r minus r prime, because I am interested only in the distance r between the two. So, in many books you will find that instead of writing it, this is slightly cumbersome to write. So, many people use the shortcut that r, capital R, is defined to be r minus r prime. So, you will find e to the minus j k capital R by capital R many places. Okay, this is the final expression. Okay. So, you saw we started with the 1D case of the string, which gave us a nice continuous function, very easy to handle. 2D case gave us a little bit more difficulty because of the integration had the Green's function had a log term. So, integrating it we had to do it carefully, and we came across a wave kind of function which we had previously not seen before with the Hankel function or the Bessel function. When we come to 3D, it got even simpler. There was nothing fancy in the integration, right, and I got this spherical 3D wave. Okay. So, if someone asks you what is the plane wave in 3D, do not write e to the minus j k r minus omega t. That is technically not right, because it just goes off to infinity, right. A 3D plane wave is usually referred to as a spherical plane wave. A 2D plane wave is a Hankel function. A 1D plane wave is what we have always studied, e to the minus j k x minus omega t. Okay. All right. So, what we have done is we started with some kind of basic motivation and went on to 1D, 2D and 3D. Chapter 14 of Balanis's book gives a very nice introduction to Green's function in all 3 dimensions. So, that you can take that as the reading material. Okay. Why is there a, okay. So,
the functional form itself changes.
Yeah. So, okay, why, okay, we can just spend some more time on this. Okay, so the question is that when we looked at 1D, 2D, 3D, why is there a different form appearing each time? And mathematically, you know the reason. The reason is each time this guy over here, the del squared guy is what is changing its form. Earlier, supposing I had a 1D plane wave, then it was just second derivative with respect to x. Now, I have this 1 by r square, all of these different terms are coming. So, that is changing the mathematical form of the equation itself, right, and that is what is changing the final result. Okay. And as far as a physical intuition, if you want for it, then it's the way in which energy has to be distributed in multiple dimensions. It depends on how many dimensions there are. So, it's a wave, it decays off to 0 as you go away from it, it's oscillatory, but how to manage this energy distribution in various dimensions gives rise to slightly different functions. Okay. Even in the case of the 2D, so look at the behavior far away, right. So, far away from the origin, you can see, I mean there's a 1 by r dependence over here, Okay. In the 2D case, what was the dependence? If you go, let's go back over here all the way, right. As I went far away from the origin, these are the far field expressions. What is the dependence like? 1 by root r, right. So, you can see that this, whether it's r or root r, and then when you go to 1D case, what is it? There is no such term in the denominator, right. So, in some sense there is, if I look at 2D and 3D, because they are truly the physical waves, it's, in my opinion, the way energy has to be balanced in multiple dimensions, 2 versus 3. That's what is giving us this different form. In 1D, yeah, 1D is a strange case. I mean, it's quite unphysical. The wave just goes on forever. It's very difficult for you to actually think of a physical 1D problem. What does that mean? There's always a second dimension involved somehow. But these graphs really, they convey the intuition of it. If you plot the 3D Green's function, it will look similar to this, right? It will have the maxima, it will have some large value at the origin and then begin to decay off. So, physically, that's what we expect. Okay, I think what we'll do is, we'll call it a quit over here instead of starting the next module on method of moments. Okay, so we'll stop here.